Thank you, everybody.
Great. How many are in the classroom? How many people in the classroom?
2, 3, 4, 5, 6.
All right. Okay.
Okay.
Good. Thank you.
Okay. Well, today we're pleased to have Ana-Sofia with us to tell us about her work on supernova type 1A photometric distance estimation, work done with Casey Mandel at Cambridge while working on a master's degree before coming here.
All right.
Okay.
Welcome, Anna.
Thank you. Is it just
Yeah. Just talk.
okay, great. Okay, so thank you for that wonderful introduction, Doug. My name is Ana-Sofia. I am a second-year PhD student in the After department, working with Doug Pinkbeiner. But I'm here to talk about some work that I did in my master's at Cambridge when I worked with Casey Mandel. It's a project that I'm wrapping up right now. And in general, I'm very interested in people have feedback or thoughts on it. Yeah, I'd love to hear it. So feel free to chime in whenever. That's how things are done here, I guess. Okay, so I'm going to spend some time providing some like astro background just so everyone knows why we're doing what we're doing and why it's important. So, let me click this. Okay, just some very broad background. We're working with supernovae here. Supernovae are stellar explosions, and specifically we're working with type 1A supernovae, which are created when there's a binary with a white dwarf and usually a red giant. And the special thing about type 1A supernovae are that they are standard candles. And I'm going to talk a bit more about what that means. But basically, standard candles, it's very interesting to us because they are the same luminosity intrinsically. And so that means that their observed luminosity relative to us directly correlates with their distance. And so precisely determining these distances to type 1A supernovae is critical for precision cosmology. By precision cosmology, I mean being able to determine cosmological parameters with very high precision. And we're going to talk a bit about more about that as well. So first, I wanted to talk about how we observe type 1A supernovae. And so we're interested in what's called a spectral energy distribution. And what I mean by that is there's 3 dimensions. There's flux as a function of wavelength and as a function of time. Because these explosions happen, of course, over time, and we're observing them over time. And this flux is measured with bandpass filters. So I have this figure on the right here, and it's showing the flux is in, the SED is in blue. So that's like the flux emitted by the supernovae, but these different filters are functions of wavelengths. So this is an example of the filters from PanSTARRS, which is the data that we're using. And there's 4 different bands, G, R, I, Z, and each of them correspond with a given range of wavelengths. And so what happens is that the spectral energy distribution of the supernova, what we observe is that spectral energy distribution integrated in these wavelength bands. And here's a GIF kind of showing how that's done. So you can see the supernova is exploding over time. So this flux is changing over time. And at every time point, we are integrating this flux distribution in these wavelength filters. So what we end up getting is a function of time per filter.
One measure.
One measurement per time per filter, per time point per filter, if that makes sense. And so, like I said earlier, type 1A supernova are standard candles. And so you can see on the left panel, this is a bunch of different type 1A supernova light curves. So you can see the luminosity is changing as a function of time. And they're standard candles because there's a relationship that we know that we can then apply to these light curves to make them all have the same max luminosity. And so that means that, like I said earlier, the luminosity that we observe directly correlates with the distance that they are at. So if you think about, the reason they're called standard candles is because like candles have one brightness. And so if you hold that candle further away from you or very close to you, the brightness that you observe will tell you how far away it is from you. And this is very interesting to us for precision cosmology. So here's an example. This is kind of an older figure, but I thought it was worth showing. Obviously, there's much newer versions of the Hubble diagram, but they're actually more complicated. So a Hubble diagram is the recessional velocity versus the distance to the supernova. And so recessional velocity or redshift is telling us how far away that object is moving away from us. And so when we plot this, it's telling us the expansion of the universe, right? Because it's showing that things that are farther away from us are moving away from us faster, which indicates the universe is expanding. And so there's this Hubble constant, this constant H0, which is giving us the rate of expansion of the universe. And so type 1A supernova are a way that we can measure H0 by making diagrams like this one. But there's a significant, what we call like H0 tension. And by that, I mean, there's other ways to measure H0 too. There's like Cepheids and stuff like that. And every different method is not necessarily returning the same value of H0. So that's where this term tension comes from, because different methods of measuring it don't necessarily agree. And that's why we're very interested in, can we measure H0 to a very precise, like very precisely? And how does that compare to other measurements of H0? And so this is the motivation for developing better techniques to analyze and fit SED models of type 1A supernova. But it's not that easy for many reasons, but one of them is this pesky thing called dust. And so here I'm kind of showing different kinds of dust that can get in the way of this measurement, because we want to measure the distance to supernova, but dust extinction can cause different wavelengths to be expressed differently, and it makes it kind of seem fainter. And so this is degenerate with distance, because we're like, is it fainter because it's farther away, or is it fainter because of dust? And so there are three kinds of dust. There's the Milky Way dust, which thankfully, thanks to someone, we know a lot about, and we can correct that using a reddening map. There's intergalactic dust.
Although to the precision you really want it, you should still be careful, right?
Okay, good to know. There's intergalactic dust, which is dust just like generally in the universe outside of galaxies. And then our supernova is exploding in a host galaxy, another galaxy, and that host galaxy also has its own dust. And so this is what potentially could have a large effect on the observed supernova that we're seeing. And so that's why we're interested in modeling this host galaxy dust probabilistically to kind of correct for that and be able to determine the distance to type 1A supernova more precisely.
And this is not enough to explain Hubble tension.
No, it's not. Like I said, the dust extinction depends on the wavelength. So here I'm showing the 4 different wavelength bands, and then the extinction as a function of wavelength. So you can see that at bluer wavelengths, they become more extincted compared to redder wavelengths. And there's 2 kind of key parameters in this extinction relation. There's RV, which is what the color bar is, and there's AV, which is where this kind of turning point is. Here, you can see here. And so as we vary RV, that's varying kind of the slope of the extinction. So that's varying how much it's varying with wavelengths. And AV is this like turning point. And here, this is assuming, in this plot, we're assuming that AV is 1 so that we can better see the relationship with RV. But what we're doing is we're actually interested in fitting AV, this dust extinction parameter. And I'm going to talk more about that.
So extinction of the statistician is the amount of dust, measuring the amount of dust impacting the stuff.
Yeah, extinction is like how much the dust is obscuring
At wavelengths.
wavelengths.
Specifically, you might say there's absorption, there's scattering, the sum of those is extinction.
Yeah.
Okay, so now this has been kind of the astro kind of introduction. Now I'm going to talk more about the BayeSN model and how it attempts to use all these things to model type 1A supernova spectral energy distribution. So BayeSN works on a per supernova basis. And so for each supernova, it has a bunch of parameters that it's trying to fit. And some of the parameters, I'm going to talk about in the next slide, are predetermined on like a population scale. But what we have is, it's a combination of like functional or principal components. So we have this first component, which is like the first like principal component. And then we have a second component that is weighted by this coefficient theta 1. And so this is what I meant when I said that spectral energy distributions have 3 dimensions, right? Because
Sorry, can you read the plot labels?
sorry.
So wavelength, time, and log.
Yeah, so it's like a surface over it's like a flux surface over wavelength and over time.
Yep.
So we're fitting this parameter which weights the principal component, and then we also have this dust extinction part that's also going into our model of the spectral energy distribution. And this is where our dust extinction parameter AV is coming in. And then we also fit kind of a residual surface. And the idea of this is that it's a surface that allows you to correct for any like differences in that specific supernova. So it's basically trying to soak up a lot of that variance. And so for that, we're fitting an entire like covariance matrix. And so the combination of all of these things gives you like a model of what you think the spectral energy distribution is going to look like, and then we can model what the observations or what the fitted light curves are going to look like. So the input
question, Ana-Sofia.
Yes.
So this intrinsic functional component, can you say is something about that? I mean, it's like why does it look so multimodal? And
yes, I'm going to talk about that in the next slide. Could you hold on?
Okay, all right, sure. Thanks.
But basically, the inputs are the observed points. Like you can see here, all these points, and then the output is a fitted SED to those points. And so we have all these, like I said, we have these principal components, these functional components, and where do they come from? And so on a population level, these are fit. And so I guess your question, Vinay, of why is it so multimodal is just because that is the functional component that was fit based on a large population of supernovae. And so these population level parameters have basically been given to me from previous analyses that people have done with BayeSN. And so what I'm doing is I'm just fitting these per supernova parameters. So the dust extinction parameter, we have this is the distance modulus, this mu parameter, which is the distance to the supernova. And then I'm fitting the intrinsic residuals and also the theta, which is the weighting of the functional components.
But
those bumps and wiggles are real, and they have been determined from on a larger population level.
Sorry, can you go back to the previous slide? Is it possible to zoom in to the axes there? The thing I was confused by was the why is it so wavy? I mean, I would imagine that actually, I'm not entirely sure what I would imagine, but I would expect that to change, I suppose, slowly or monotonically with time at least.
Yeah, well, it doesn't necessarily change monotonically with time. As I showed this GIF before,
Yeah,
this one, right? There's an explosion, which will increase the flux, and then we were looking at how it decreases after that explosion.
and this is just one filter.
Yeah, this is just
this
is just one filter.
You're plotting more than one filter on the
Yes.
right? So in your
you can think of this of the GIF. If I go back, you can think of this as one slice through. If you just take one slice through at a specific wavelength,
right?
Or wavelength range, and then we're going to see that.
So when you're plotting wavelength in your model, you plot the smooth curve, or you plotting just the points? No, these are smooth SEDs, right?
Yeah, these are smooth SEDs. So we're modeling the SED, but then we have to kind of take those slices to fit it to the observed points, because the points that we are observing are in these integrated bands.
Right.
But we are modeling the entire SED and then matching that to these points that we have observed.
Does theta 1 have a physical interpretation here?
Not
It's just a
necessarily.
factor.
It's just a coefficient of the.
Is it the amount of stretching of the?
Yeah, it is correlated with the slope of the SED kind of, but at least I don't necessarily think about it as super physical.
Okay, but I guess I'm gonna. So you said a few slides ago, some fall faster and are faders, some fall slower and are brighter. Intrinsically, and has that correction been applied? Has that all been taken out before you're doing this, or is that getting absorbed into these components?
Are you asking is that correction is happening already?
Yeah.
I think I'm actually not sure. That's the question.
Yeah. Just curious whether this needs to account for that, or whether this is correcting higher order things kind of after.
Actually, I think it is correcting for higher order things, because we're assuming that they are standard candles already. So we're assuming that correction is already
standardized.
Presumably.
Okay. Sounds good.
Sorry, another follow-up, still on that intrinsic function.
Yeah.
So why is there no confusion between for example, the extinction law versus this intrinsic functional component? I mean, why couldn't you trade off variations in those two?
Well, the functional component is fixed for all, across all of the supernovae, but the extinction, we're fitting on a per supernova basis, if that makes sense.
Ah, okay, understood.
But you're
Okay,
fitting the
I was missing
amount
that.
or the
Okay.
whole law.
We're fitting the AV parameter specifically.
And you're assuming dust in distant galaxies long, long ago looks like dust in the Milky Way today. Pretty much.
Pretty much.
I mean, you have to do something, but that is also an assumption to stay.
Yeah.
Here it looks like the dust extinction is a subtractive component.
Yeah.
I would have assumed that it's just like a, I don't know, just multiplying. It's like,
Well, we're multiplying. Well, I think because it's like extincting, we're like removing flux, right?
Is this all done in log flux?
yeah.
Because you
Yeah.
labeled your actual
Yeah.
log flux.
Yeah.
It is.
Yeah, it's
Yeah.
a lot of fun.
Otherwise.
Yeah.
Yeah, and this is not my figure, this is a figure from like a broader BayeSN paper. So yeah. Okay, so I guess just to reiterate, the parameters that I am particularly interested in and that I'm going to show results about later are this theta parameter, this dust extinction parameter AV, and distance modulus mu.
Which is some horrible astronomer long distance thing. But
Yes. Okay.
It has to be log of course.
So I guess we will get the distribution of uncertainties on this new parameter.
Yeah, so we're interested in the uncertainties on all of these parameters, which I'm going to talk more about. But I guess for cosmological purposes, and I guess for other astronomers, they're most interested in being able to like estimate this mu parameter well. And that's for the precision cosmology application. That's what people are really interested in. But I mean, we argue that, especially with the dust extinction, that needs to be modeled well too, in order to properly fit the distances.
And I mean, this graphical model is helpful, but then you've got a ZSC, is that like corrected redshift of supernova, or?
Yes, I think so.
And then it's going, like, I'm not sure what this is, but it's going to a ZS and also going to the distance mu.
Yeah, I mean, the distance modulus, the redshift implies the distance also, right?
I mean, I guess if you're kind of modeling forward and saying,
Mhm.
here are my parameters, and how do I get, a generated model of the data that agrees with the data.
Mhm.
But like you measure the redshift, you want the distance.
Yeah.
So,
And I mean,
yeah, okay, anyway.
there's a lot of thing in like other people with supernova, they're interested in using photometry to estimate the redshift. But we are using photography to estimate the distance. Okay.
Yeah, okay.
So S is spectroscopy. Oh,
S is per supernova. So
no. Oh, yeah. So the redshift S. Okay.
Yeah. Okay. So now I'm gonna move on to talk about variation inputs. Okay. So I guess previously, like BayeSN has been around for a while, and people have been using it to model type 1A SEDs for a long time. Their current iteration uses Hamiltonian Monte Carlo to fit the posterior distribution. But we were interested in using variational inference, mostly because it provides a computational speed up. That was the biggest motivation. But also, I think it's worth noting that variational inference, I'm going to talk more about it later, but it provides an analytical form of the posterior that using MCMC methods doesn't. And that can be interesting also for like further analysis. And the main motivation for this, other than that people just want faster analyses and that being able to analyze more supernova can help you constrain parameters, is that looking forward, there's more missions like LSST and Roman that are going to provide significant quantities of data, way more than we currently have. And so there's been a significant push in trying to get analyses that are more scalable to larger and larger data sets. So an overview of VI or variational inference. So the aim is to approximate a posterior by optimizing the parameters of a given functional form. So MCMC doesn't assume anything, and it just fits the posterior distribution. Basically, the way that variational inference is faster is because it assumes a form of the posterior, and then it optimizes the parameters of that form. And so this is an example. You can see if we have some posterior, this like blue distribution, if we're assuming that the posterior is a Gaussian, then we can just optimize the best Gaussian that fits that posterior distribution. So this is the example in the green. If we're assuming a Gaussian, that is the posterior that we're going to get. And so you can see that we are getting the best posterior by minimizing the distance or KL divergence, but you can think of it as the distance between the approximate posterior and the true posterior. And so we are optimizing the parameters. So this is this Q of Z and Q, big Q being the like functional form. And then we're optimizing the parameters in that functional form to get our best posterior estimate.
So just a quick question. It's a general question about variation inference. I think it's important to recognize at this stage. If we're going to do that, which the posterior is effectively in this case is a normal, right? Why not view that as just the way, not as a variational inference, but as the say, I initially did a more simplified model and in order to do the computation. What's the difference being viewing that is a modeling approach instead of the computational approximation?
I mean, I guess you can think of it as a modeling approach in a way that we are assuming this form of the posterior, and that is a conscious decision. That is like a modeling decision that has been made. I guess the reason why people think of it as computational is because you don't necessarily, like with MCMC, you're not making any sort of assumption. And so the trade-off is, computational speedup is a trade-off with this assumption of a functional form. And I guess you can think of it as a modeling decision in that you have to pick a form of your posterior that you think is going to work, given your model.
Right, but there's an important distinction here, right? Because if you think about the modeling, if you think that's a modeling approach, you probably start to criticize the model a lot because, you know, all the kind of assumption you're making, which is say not realistic, you know, it's not normal, it's asymmetric. You will have all these model criticism comes, which, you know, helps you to understand where the things will fall. But if you just treat it as a computational approximation, the mindset is say, oh, you know, it's approximation, it should be okay. But is it like, is this kind of a thing actually undo all the careful thinking into the modeling? So I just want to see if there's some subtlety there that actually it's not. And so, you know, it's a more broad question in terms of thinking this as a modeling or as a computational approximation. But in the end, your results will be all based on this actual computation approximation you did, right? Because that's the whole point, right? So
yeah, you're right that there is a trade-off there. And if you pick, basically your approximation is only going to be as good as your decision about what functional form that you're going to use. And I'm going to talk more about that when I get into what I've done in the results. But it is a conscious decision, but you're making that decision about the form of your posterior. And it's not necessarily how you're modeling. Well, how you're modeling the parameters is going to inform that decision.
So just to be clear here, Z is not redshift, it's the parameters of the Gaussian.
Sorry, that was probably
right. Okay.
a bad decision. Yes, here Z is the parameters.
And that means you're taking the DKL between QZ, which is your simplified Gaussian model, and P of Z given X,
which is the true posterior.
Actual posterior.
Just commenting on Charlie's question, I think there's the additional point of non-convexity, right? So if you have a posterior that is non-convex, this might be really hard to navigate through, right, to fit. But if you do variational inference and just assume, for example, okay, it's like locally Gaussian, then you could probably like improve convergence.
Yeah.
So I think this is probably.
That's a good point.
Yeah, I'm sorry, what I studied wrong. Here Z actually is you are looking at a redshift distribution, right? You're saying given my data on this object and all my prior assumptions, I have a distribution of redshifts that are allowed by the data.
No, here I mean Z as just the parameters broadly, all of the parameters.
I can ask you later.
So yeah, sorry. So here, like X is the data and Z are the parameters.
Pick up different label.
Sorry?
Pick up a different label next time,
Okay, that's fair.
I think.
But yeah, and so in practice, in variational inference, you use the evidence lower bound, or it's called the elbow, as the loss function. And so this is the function that you're actually optimizing when you're fitting the distribution. Okay, so one of the problems that we've had when we're using variational inference is that specifically fitting AV, this dust extinction parameter, can be tricky because of these like physical modeling things, right? And so currently BayeSN uses an exponential prior on AV. And so this leads to a log normal form in the posterior. And so I've plotted a log normal, I've shown a log normal here just so you can see. The problem is that physically, we want AV to be positive, but it can also be very close to zero, and it could even be zero. And so log normal is not a good approximation in that because it forces zero density at zero. And so we're interested in having a posterior form that constrains AV to be positive, but allows non-zero density negligibly close to zero, while also still having a full rank covariance matrix, so that AV can fully vary with all of the other parameters. And so to do this, we started looking at what's called a zero lower truncated normal, or ZLTN distribution. And so this is just a normal distribution, except you truncate it at zero on the left. And then you can just see, this is just showing that that density gets like reintegrated into the other side so that the normalization is still accurate. But what this does is that it allows for non-negligible density at zero. And that's important. And I've shown this is the functional form here, but it just shows that it's a normalized function, basically. And so we decided that we wanted to try using this zero lower truncated normal distribution specifically for AV. But we still wanted all of the other parameters to be Gaussian. And so we're trying to fit, it's like a multivariate normal, but AV is truncated and all the other ones are normal. And so we created this multivariate zero lower truncated normal distribution. This is kind of in the weeds, but basically I was just showing how we did this. You can do this by taking, if you have like a multivariate normal distribution with some mean vector and some covariance matrix, you can partition this into like chunks. Like you can, here we're interested in, let's say the first one is AV. And so we can take the AV mu and then the mu vector of everything else. We can partition the covariance matrix the same way, where this is the covariance of the variable you want to truncate, and then the other ones are, split accordingly. Then if you sample that truncated parameter with the truncated distribution using these parameters, let's say we get some value A, then you can calculate the conditional probability of all the other parameters using this function where this mean and covariance matrix is a function of this value and also these like partitioned sub-matrices of the original covariance matrix. And then you can calculate a joint probability. So basically I'm showing how you can have a distribution where one variable is this zero lower truncated normal distributed and all the other ones are regular Gaussian distributed, and you can model them all jointly. And so this is what we were interested in seeing, how if this is going to improve the fit for these supernovae.
And just to be clear, when is a truncation, you only truncated one variable?
Yeah, we're only truncating one variable.
Okay,
We're only truncating the AV parameter.
Okay, so it's only one, it's a univariate truncation, then the rest of them are still condition on that value.
Yes.
It's still Gauss, it's still a multivariate Gaussian.
Yes.
Okay, correct. Got it.
Good. Okay.
I see. Yeah, I think he's asking the same thing. I was
Yes.
wondering, because I'm like, if you start with something truncated, you can't end up with a posterior that's described by immunity covariance.
No, so we are.
But conditional
on
a draw of X1
yes.
from that distribution, then you can.
So everything else is normal.
I'm with you.
Like Gaussian full covariance matrix, just one of them is truncated.
Yeah.
Okay, and so just as a comparison, I wanted to talk, we also looked into something else. which is the Laplace approximation, which is where you Taylor expand the log likelihood around the maximum likelihood estimate. And then you can approximate likelihood as a Gaussian centered at the maximum likelihood estimate. And so you can see these are just examples that sometimes it works better and sometimes it doesn't work. But this is kind of a point of comparison for us, just another way to estimate the form of the posterior.
How high is the dimension here?
Yeah, that's a great question. So we are fitting 28 dimensions. And the reason why all of those dimensions are happening is because of this covariance matrix. So we're fitting like this theta parameter, we're fitting the AV parameter, we're fitting the distance modulus, but we're fitting a covariance matrix with all the values, and that's what's bringing the total dimensionality to 28.
Okay. The reason I mentioned this is it's known that this Laplace approximation, or sometimes they call the saddle point mission, in high dimension has a different form. There's a correction factor. There's a paper done by Peter McCullough and his students in Biometrica, I think it was 1980-ish or something, shows like the standard approximation is actually a bit off because of the high dimension. So there's a little correction factor. It may not make a big difference, but just want to mention.
Okay, no, that's actually good to know. Thanks.
Yeah, it's a Biometrica paper, Peter McCullough. I think his student is Shen, S-H-E-N. Don't remember exactly.
Okay.
Okay, if you can find it, let me know, okay?
Yeah, okay, thank you. Okay, so these are some of the like posterior forms that we're going to try using variational inference. And so now I wanted to talk a bit about just the details of the implementation. So I'm using NumPyro, which is a probabilistic programming language that interfaces with PyTorch and also with JAX. And JAX we're using for this just-in-time compilation and vectorization. The idea being that it's just going to be a lot faster. And this is also using Matt Breland, who's a postdoc at Casey's, has done a lot of work with that NumPyro and JAX implementation of BayeSN. So total, I'm going to compare 4 different types of posteriors. I'm going to calculate like an MCMC, regular posterior, and then I'm going to calculate the Laplace approximation. I'm going to calculate using this zero lower truncated normal, like multivariate zero lower truncated normal, and also for comparison, just a full like multivariate normal. And in practice, I found that these perform better when they're initialized on the Laplace approximation. And so that's just a step that I do. I start the Laplace approximation, the like median values of the parameters, and then I train these forms using it's also, I should say, it uses like stochastic gradient descent to optimize this elbow, the evidence lower bound parameter that I talked about earlier as the loss function. And so I tried it on 2 different kinds of data. And so there's the foundation data set, which is a data set of real supernovae. It's 157 type 1A supernovae with Z less than 0.08, so low redshifts in the GRIZ bands, and it's taken with the pan-star cell scope, which you can see here. But I also have a data set of simulated supernovae that I simulate with parameters sampled from the priors. And the idea of these is that I know the truth. And so I know the truth, I simulate them, and then I fit them. That gives me a lot more power with what I can look at. So, okay, so that's all of the background. Now I'm going to talk about some results, what actually happened. So about the training parameters, this might be a little bit in the weeds, but just talking about like the number of samples we took with MCMC chains, 250 warm up, which you then discard and take 250 more across 4 chains to get 1,000 samples. And this is per supernova. So per supernova, I'm taking 1,000 samples. NumPyro has built what's called AutoGuide, which is basically you can specify a functional form and a model, and it will fit that to the model. And it has built-in AutoGuides for the Laplace approximation and for multivariate normal posteriors, which makes sense because those are pretty common. It does not have AutoGuide, obviously, for this multivariate truncated normal distribution. And so I wrote my own AutoGuide to do that. And so I run them on the Laplace approximation, and then I run more iterations for these 2 based on the Laplace approximation. And here's just an example. It's like you're optimizing the loss just like in any other kind of machine learning, but this is like stochastic, right? And so the loss isn't going to monotonically decrease. And you can see here that there's a lot of bumps and wiggles in there.
Okay. They got a lot of bumps and wiggles. Is the proposal distribution too big or something?
The proposal distribution?
Oh, I think that's what you do too. When you do this comparison graph. So you see the fluctuation. It depends. I mean, this is not dimension you're looking at. But it is fluctuating.
It looks a bit large, but this is just intuition.
And you to have a longer.
I have like tried to optimize, like there's like the optimizer and the learning rate and these things that I have tried to optimize, but I'm definitely getting to stochasticity. But as I'm going to talk about later, I don't think it actually matters that much.
I mean, that's for the MCMC, which is a straw man that you're setting up.
No, this is
Or sorry, this is
an example of like fitting.
For CLTM?
Yeah.
Oh.
So question about the MCMC.
Yeah.
So you only have 250 times 4
Yeah.
iterations. But then, how do you know? I mean, is that enough? I mean, that seems like awfully small for MCMC.
I mean, this is what's like been determined by other people using BayeSN with MCMC. I think we've just been going with 1,000 samples per supernova and then using that distribution going forward. But if you guys think we should use more.
It's small. I agree with you.
Okay.
So do you happen to have trace plots or something?
Casey's online, right?
Oh, is Casey online?
Yeah. Ana-Sofia, aren't you using what's the MCL thing? It's called? It's the no U-turn sampler where it already automatically thins the chain to that's the effective sample size, right? It's not the raw sample size, it's the effective sample size.
Okay, that makes sense.
Okay. That's an important difference.
Okay, thank you for saying that. Okay. That's good.
Yeah. Okay. That's it.
So can I ask a follow-up question? Ana-Sofia, for the cases of the VI, you're using essentially stochastic gradient descent where the loss is the elbow. The randomness comes from the batch size, right? On each iteration of the gradient descent, you're only showing
that it's calculating based on like dynamic batching. So it's not actually calculating the elbow on the entire data set the entire time.
Oh, okay.
Which is just how
So if the batch size was the full data set, then there will be no stochasticity, right? Because you'd be seeing the same examples each time in each iteration.
That's a good point.
Okay, good. So in that case, I'd be very tempted to, I mean, you batch for very good reason, of course, but 1 in 100 times you could do something like that's just calculate the loss on the whole thing.
Sure.
And make sure that's kind of monotonically decreasing or hopefully converging to some value.
Okay.
Because if the loss over the whole thing were jumping around that much, I would be very concerned. Right?
Okay. Yeah, actually, that's a good point.
My question was actually related.
Okay.
This is a question.
Good.
Okay. So I wanted to show these are like kind of case study fits. So from the foundation data set, I picked 2 supernovae, one that has a higher AV dust extinction parameter and one that has a lower AV, like very close to 0 AV dust extinction parameter. And the reason is that really the like differences that we're going to be seeing are at these extremely low AV supernovae, right? Because this truncated normal, if it's far away from 0, it's just going to be a regular normal distribution. So we're interested in this behavior really close to 0. So this just shows that for everything else, it seems the 4 different kinds seem to fit reasonably similarly. But if we zoom in on this, so this is this panel here. If we zoom in on this AV marginal distribution, we can see some very subtle differences. And I think it's hard to see. I need to increase maybe a bit like this. But anyway, but we can see that the MCMC goes very like close to 0. And then the 0 lower truncated normal goes similarly close. But we can see this kind of log normal behavior in the multivariate normal and also in the
That's blue or black.
That's black.
So the black one's above 0 at negative values?
I have to look into this. I think it is like extremely I think it might just be at 0.
Because I thought maybe this one would be right, because this one's allowed to do that, isn't it? If I understand what you're doing.
Well, this one uses the exponential prior, which is going to give us like a log normal. So
okay, so this should be strictly
these are enforcing 0 at 0. Well, these are enforcing. It doesn't have to necessarily be 0 at 0.
Just could be plotted the way you plotted. Yeah. Okay.
How do you get these samples for the other cases? Because I mean, you do stochastic gradient descent to
Yeah.
get your approximation, and then just
Yes, so we find
then
optimize the
compare.
parameters and then we sample from the posterior given those parameters. From the form.
Just for the comparison.
Yeah,
Yeah, okay, yeah, that makes sense. And in the MC case, you sample directly from the posterior.
Yes, yeah.
Mhm.
So then this is just a case study of one very low AV real supernova, but I have all these simulated supernovae, and so I wanted to do a comparison with those and see how they go with the different methods. And so this is a comparison. Basically, I'm comparing so I have these 4 methods, right? But I'm very interested in how they compare to MCMC, which is kind of our baseline. So this is a comparison of the Laplace approximation compared to MCMC. So I'm going to go through what these panels are. So this top row is just a comparison of the values. And this is comparing on the x-axis are the true values because I simulated these. And so I have the true values. So these are comparing and these are the medians. So when I take a distribution, I take 1,000 samples. What I'm plotting is the median is the point, and then standard deviation is the error bars. So I have the comparison of the value, the median value from the Laplace approximation for mu, for theta, and for AV, compared to the true values. And then in the second row, I have the residual. So the difference between the median and the true value. So this is just the difference. These two subtract against each other. And these are compared, this horizontal line is 0 for comparison. And so this is for, again, mu, for theta, and for AV. The AV I plotted on a log scale so that we can really zoom in on the behavior at very low AV, which is why this is kind of curvy. And then in this bottom panel, I'm plotting the residual, but compared to MCMC. So this is the Laplace approximation medians versus subtracted the MCMC medians. And so this bottom row is what I'm particularly interested in, is this comparison with the MCMC values, which is previously what we had been using. And so you can see that the Laplace approximation is pretty biased, right? It's like overestimates AV, underestimates the distance modulus, and underestimates this theta parameter. And you can see also here some of these, like the blue points are higher than the red points, although it's kind of hard to see. And so then I can do the same for the 0 lower truncated normal distribution. You can see it's exactly the same. It's a comparison of medians compared to the true on the top for mu, theta, and AV, and then the residual against the true for mu, theta, AV, and then the residual against the MCMC for mu, theta, AV. And so we can see that for mu and theta, it is a lot less biased than the Laplace approximation, which is good, but it does.
Question, Anna?
Yeah.
So why is the spread so different between the middle and the bottom rows?
The spread with like this.
The scatter.
Yeah.
The vertical scatter.
Yeah, that's a great question. So this is the difference between the approximate values and the true values. And this is the difference between the approximate values and the MCMC. And it's because the MCMC is not perfect. It does not always estimate the truth. And you can see that the red lines are MCMC. And you can see that there is a lot of scatter even between the MCMC and the truth. So this is another question that comes up is like, should we compare to MCMC, which is our like gold standard in practice, or should we compare to the truth in the simulations? I mean, ideally, we would find the truth from the simulations, but in practice, even the MCMC doesn't find the truth in the
simulations. Shouldn't that mean that the bottom panel, let's say the theta, the spread should be larger than plus minus 0.5?
Well, the VI approximation is close to the MCMC, which are both further from the truth. Like,
okay, I see. So they're not They're not IID. So okay.
Yeah, the LTN and MCMC are making the same mistake basically.
Yeah, exactly. Okay. And so that's the question of, should we try, like, is it good enough to just be like the MCMC? Ideally, we'd be getting the truth, but in practice, right? This is an interesting comparison, I think, to make.
Thank you.
Can I ask a question, Ana-Sofia?
Yes.
So is it clear that the bias at the 0.01 AV level relative to MCMC is actually a bias relative to the truth? I mean, the scatter in that truth plot is so large, I can't tell.
So, say that again. The scatter at low AV is scatter relative to the truth, is biased relative to the truth. Yeah. And this is because we're constraining AV to be positive. And so at very low AV, like it can really only overestimate AV, if that makes sense.
I guess I'm just worried.
Underestimate it.
Yeah.
I guess I'm trying to understand how worried I should be about the bias in the bottom panel. I think the answer is not very worried because I can't see it. Yeah, there, exactly. Yeah, because it's not that biased relative to ground truth. I mean, and it's biased at the 0.01 mag level. I mean, is that?
Yeah, I mean, I think it is definitely still biased. And I think what worries me a bit is that the bias doesn't necessarily even out as we go to like higher values of AV, where it should be able to more equally underestimate and overestimate.
But it's biased relative to MCMC, which is also wrong relative to ground truth. Like, is that a larger bias relative to ground truth? It doesn't look like it to me.
Yeah, that's a good question, and it is honestly not that easy to tell.
Yeah, the colors are maybe.
It's
It is hard to distinguish, but as later I'm going to talk about other ways that we can probe the bias compared to the ground truth also.
Okay, maybe I'll let you do that. But I ask one follow-up question, which is, this is sort of showing that the modeling isn't perfect, the larger scatter in the second row versus the third row. Does adding RV variation help? You talked about RV at the beginning. If you fit RV as another free parameter, is that overfit? Does it help resolve the scatter? Have you tried it?
But this is all simulated, right?
These are simulated, yes. All of these are done with a population RV, with like a global RV that has been predetermined that I'm not fitting. However, with BayeSN, you can also, you have to fit those population level parameters, and that's like a whole kind of separate ballgame. But that's an interesting question of floating the RV, and I think maybe other people in cases people were thinking. I don't know if Casey has.
Okay. Thanks.
I was wondering about that constraint on AV. I mean, like physically, of course, you want it to be positive.
Yeah.
But statistically, it doesn't have to be, right?
This is a great question. Yeah, and so it's this concept of like, can we model unphysical values? Right, because if we modeled it as like a Gaussian and we let it go negative, and this is work that I've done in the past, which I did not include here, but if we let it go negative and we just take the positive values, could that work in practice? Yes, would it be, but that's not like necessarily physically motivated, and so this is a trade-off that we have to think about. I don't know, Doug, do you have thoughts?
I definitely have thoughts. I've been biting my tongue to not make the comment I always make when this comes up, which is you should apply your physical priors at the point where you do physics, but before then it's just a math problem. And I have no problem with negative AV if we're just solving a math and statistics problem.
Okay.
Obviously, that doesn't mean you think there's literally negative dust.
Yeah.
It's just saying you apply the physical prior at the point you make the physical inference, which is not yet.
Yeah, that's true. That is something and that's something that I've explored in the past. When I was, it's in my thesis, but I didn't include it here. Is like using like an asymmetrical loss approximation. So like that is like two exponential functions back to back, right? That also so if you like change the parameter of that negative one to be like just let it go like a little bit negative and keep most of the probability density in the positive. That could also work.
But I would also, at least as a straw man to compare to, just be the dumbest possible thing.
Letting it just fully normal, let it go negative.
Yeah, you've got a multivariate Gaussian.
Sure.
I mean, of linear dust and linear flux, not log.
Yeah.
And just let it go negative if it wants.
Okay.
If the data drags it way negative, you know you've got a problem.
Yeah.
Because it should never be significantly negative.
Yes.
Yeah. But if it goes a little bit negative, fine. And then downstream, you decide how you're going to interpret that. But it's just, having this chewed out of your distribution kind of does irreparable damage to the subsequent inference, I think. I don't know.
Okay.
It's an interesting thing. This comes up all the time, right?
Yeah, we have exactly the same problem in high energy or like in gamma rays, right? Where people try to measure flux points. And the question is like, okay, do we constrain it to be positive, right? The flux that you measure.
Yeah.
And I mean, if it goes negative, then it typically hits the background system. So, okay, there's part of the analysis or the modeling that you have not understood yet. And you can either take that into account, I don't know, by trying to handle the systematics, or you just say, okay, force it to be positive.
Yeah, but if you sweep it under the rug, you might not ever actually get to the bottom of your problem.
Yes.
Yeah. It's an age-old debate. We should let you go on.
Yeah.
Okay. Are we?
Yeah, we
have like
have, yeah, it
amount of
would be
time.
good to finish in like 10 minutes the last.
Okay, okay. So this is the same for the multivariate normal. I'm gonna keep moving. But basically, I think it is not that biased in mu, which is good. Like also, this is not that biased in mu. And in practice, we're very interested in the parameter estimates for mu. Okay. And also, I fit the foundation data set. And so we can make like a Hubble diagram and look at the Hubble residuals. And this RMSE value, we compared it to previous analyses with BayeSN, and it seems to be around the same. And this is using the zero lower truncated normal variational distribution, variational approximation. So I have all of these variational approximations. I can make all these plots with points that you can't really tell the difference. But we're very interested in how do you actually evaluate variational approximations other than making these kinds of plots and looking at the differences. And luckily there's a paper exactly about that from Andrew Gellman's group, who is kind of big in statistics. And so basically this paper proposes two different kinds of metrics that you can use to evaluate and validate the effectiveness of your variational approximation. So the first one is what's called Pareto Smooth Importance Sampling, or PSIS. I've included the algorithm here in case people want to look at it, but the basic gist of it is you have all these like samples from your variational approximation. You can calculate the importance ratio, which is the ratio of the true joint density ratio to the probability from your variational approximation. And so then the way this works is you have all these important ratios for all of your samples, and then you fit the distribution of these ratios to a generalized Pareto distribution, and you get the shape parameter, this K value. And so then the claim is that you can use this K value to determine if the convergence is good and if your VI approximation is good enough. And so the rule of thumb presented in this paper is that if the K hat value is less than 0.7, then it's like good enough. If it's more than 0.7, it's not very good. So yeah, so I tried calculating this parameter in a bunch of ways, but I found some weird behavior. And so one of the things I tried was that when I'm training at every iteration, I calculate, well, not every iteration, but every set number of iterations throughout the training, I'm calculating this value. And I found kind of weird results, which is that this value varies a lot. And so if I stop this training at any point, I could get any value from like K equals 0.5, which is supposedly really good, to like K equals over 1, which they use the word catastrophic in the paper for if it is over 1. So that's like really bad. I found all this weird variation, and I'm not really sure why. And I'm not really sure if this means that I can trust this parameter, this like value really to say whether my variation approximation is good or bad. And so what I did, we talked about my like loss plot and how there's some variation. And so what I do is I just fit for like 30,000 iterations, and then I take the parameters of those last iterations and I proceed with those. But I was like, maybe,
quick question.
Yes. Yeah.
So you already expressed some skepticism about using 0.7 as this criterion, but do they provide any sort of physical reasoning as to why that would make sense? The reason I ask is that we find this 0.7 in several astronomical situations. So it's very close to, for example, the flare distribution on the sun. So why?
Okay. So there's no physical interpretation because this was a statistics paper. And this is purely just presenting the statistical analysis. And personally, I don't think that there's any necessarily physical interpretation of this shape parameter of the distribution that you fit. But that is interesting to know.
Okay.
Is it just 0.7 is an example of a number between good and catastrophic?
Well, there's like a scale. Like they say less than 0.5, they're like, that is very good. Less than 0.7 is pretty good. Above 0.7 is bad. Above 0.1 is like horrible.
Yeah,
they have like this
exponential.
Yeah.
Okay.
Yeah. But so as I was saying, I have my loss. I just take the last parameters, but I was like, what if I actually go through those and I pick the best loss and I take the parameters from that one? What is that difference? And maybe would this fix my problem? And so what I do is I compared the K-hat values that I calculate from these best parameters versus the last parameters, which I'm using. And so this is a plot of the K from the best loss, the K from the last loss, and then they're colored by the difference in mu. So I'm asking, like, does this actually make a difference in terms of the estimates that I'm getting in the parameters? And it seems like no. It seems like no, and also the variations are not that big. But so I'm kind of confused. And if anyone has ideas about this like PSIS metric, because I'm finding that, and so one of the things that I'm thinking is that maybe my dimensionality is too big for like this k-hat to actually work well. I do see I dove into the other papers from that group about this, and they have plots where they show that it varies some also. But basically, I'm not necessarily finding that it is a very reliable, I guess, estimator for my purposes.
So what happens if you take the entire data set at the last value and calculate K?
The entire data set, like with no backing?
Well, because in your stochastic gradient, you do this groups of divisions. Right?
Yeah, the batches.
So the batches, yeah. So when you take the
I can
calculate K from everything.
I can look into that. Yeah.
But
you would think that it would be more uniform.
Yes, that's there is a parameter.
And so this PSIS metric is evaluating how close is your variational approximation to the true joint density, right? But they also present a second diagnostic, which is called variational simulation-based calibration, which I think is a lot more interesting because it is evaluating your marginal distributions. And so the way it works is with simulations. So you simulate a bunch. Here I'm simulating a bunch of supernovae with true values that I know that are drawn from the priors. And then I fit the simulations with VI, and I generate the samples, which I'm already doing. And so then what you do is you calculate the probability of the samples being less than the true value. So in practice, I have 1,000 samples. I just calculate the number that are less than the true value. And then you plot the distribution of these probabilities over the entire population. And the idea is that this is going to evaluate bias in your marginal distributions. And so these are the results. So basically, the columns are the different posteriors, right? So this is MCMC, this is the zero lower truncated normal, multivariate normal, and the Laplace approximation. And then the rows are the distributions of the probability for each parameter. So this is for AV, for mu, and for theta. And don't necessarily be alarmed about how the edges are very high, because this just means that for some of them, all of the samples were below the true value, or all the samples were above the high value, or higher than the true value. But what we're interested in is in this distribution, right? If all of them are skew more towards being lower, then that's a bias that we don't want. And so here I've plotted, so I have all these distributions. The black line is 0, just for centering purposes. And then this blue dotted line that I plotted is the median. And that's just because I thought it was good to plot just by eye. But you can calculate the p-value. So what you do is you do a two-sided KS test of the distributions of p and 1 minus p. And this is going to evaluate how symmetric is the distribution, which is what you want. And then you can get these p-values, which tell you how symmetric is the distribution or not. And so p less than 0.05 means that it is not symmetric. And so here I've highlighted the ones that have p-values less than 0.05. So this would suggest that for multivariate normal, AV skews high. And for the Laplace approximation, it also skews high. And this suggests that for the zero lower truncated normal, theta will skew high a little bit. But this is an interesting way, I thought, of evaluating the bias in the marginal distributions of these different variational approximations.
So is there meaning to p if p is much smaller?
Yeah, so if p is less than 0.05, you can draw the conclusion that it is that p and 1 minus p are not drawn from the same distribution, which is what the KS test is evaluating. And so that means that it is. I mean, p-values are but
it's interesting conclusion, because when you look just by eye, then they don't look very different.
Yeah.
So I'm just wondering if this edge is close to the one, so the edges dominates your p-value.
Yeah, and I mean, if a lot of them are varying in one direction, right, then that can that's true. But I thought basically that this and the PSI, I think it's interesting to have metrics to evaluate how effective your variational approximation is, and not just stop at this is what I got. So I thought they're interesting.
Yeah, that's very interesting.
So yeah, that's pretty much all I had. I'm gonna leave my conclusions up there. Basically, I think that VI is promising. I think it can definitely rival MCMC. I don't know if it's necessarily better, but it is definitely more scalable. And we have to remember that my use case, which is like this like zero lower truncated normal to approximate AV, is a very specific use case. And I think more broadly, people that are just running MCMC don't necessarily need that. And so broadly, I think VI could work well for people that are just running MCMCs with things that like a multivariate normal, even low cost approximation for a lot of people's purposes would work really well. And I think it's an interesting middle ground in that it's scalable, but it's still using your model and still interpretable, and you're not fully throwing away the model and going to machine learning. So
computational time.
Yeah,
much more efficient.
And so it is anywhere between like 2 and 5 times faster. You have to take this with a grain of salt because it is depending on how many like samples you're running your MCMC for, and also how many iterations you're running your variational inference for. But for these comparisons, that's what I found. But that being said, you saw my loss function, it kind of was low for a long time. I could probably scale back the number of iterations that I'm training the VI for and probably still have similar results. And that would take down the runtime too. The other thing to note is that 2 to 5 times faster that I quoted also includes MCMC being fit in parallel across 4 cores, but the VI is only fit on 1 core. So it's also like computational resources and also time.
So is it right that you need 1 core because of the stochasticity of the gradient?
Yes.
Okay.
So yeah, that was all I had.
Question about the ZLTN.
Yeah.
Oh, maybe Casey had his hand up. Sorry. Go ahead, Casey. I'll ask after you.
Yeah, thanks for the talk. Now I can remember what you did. So yeah, so it's like 3 o'clock, 4 o'clock in the morning here in Australia. So I'm just getting my head wrapped around this. Yeah.
Thanks for coming, Casey.
So you have a noise, your loss function, as you mentioned, doesn't decrease monotonically, it jumps around. Yeah. And that's actually due to 2 reasons, not just one. One is that in your stochastic gradient descent, you are using batching. So you are at each iteration, you're showing, you're actually optimizing on a subset of the data, not all of it. Is that right?
Yes.
The other source of randomness is that to evaluate the loss function, which is the elbow, the evidence lower bound, you have to calculate an expectation of the log posterior with respect to the surrogate posterior, right, the guide. And you actually do that with samples, right? You sample from the current surrogate posterior to calculate expectation. And then you have to evaluate that. You average that over the sample, so you calculate like a numerical estimate of the expectation. And so you have to choose how many samples to draw from your current.
That's true. So this is the
surrogate
parameter you can tune as well, like a hyperparameter you can tune for the VI.
So in principle, if you just try to improve your numerical estimate of that expectation, the elbow, by say, instead of using 10 samples, you use 100 samples, then your estimate of the elbow should be less noisy, right? And then that, have you tried seeing if that stabilizes that?
Yes, that is something that I have looked into. However, there's a significant trade-off with, like, it takes a lot longer to run when you're using more samples in the elbow calculation.
Yeah.
So that is something that, so I tried using more and then I tried using less. And I found something in the middle that kind of works, but this is something that you can tune. That maybe I can tune more as well.
Right. So I guess it's the trade-off between, say, like if you wanted to use that Pareto index as a measure of the accuracy of the VI fit, there's a trade-off between doing less computation and maybe getting a less accurate fit versus doing more computation and getting a better fit. And it kind of depends on what kind of precision cosmology you want to do, I guess.
Yeah.
Okay. We have a question here in the room.
So can I ask my truncated normal question?
Nina, can you wait? There's question in the room. Okay.
Okay.
I mean, I guess every parameter is important in the modeling, but is there like some sort of like more importance to some parameters? Because just going back to the previous slide, we were seeing that the p-values were like always very high for like the mu parameter, which I'm sorry, I didn't really understand what it's about, like the mu parameter. But so is it the concern that like, even for the MCMC approach, which seems to be like the common approach right now, like it is a concern that this particular parameter is like not satisfying such requirements. Like, I just understanding the importance of parameters in this.
Yeah, so I think for cosmology purposes, the parameter that a lot of people are most interested in this mu parameter, which is the distance to the supernova. And on all of these show that the p-values are high. And actually, like a high p-value is good in this case because it's telling us that the distribution is symmetric. It's like the p-value on if the distribution is not symmetric. It's kind of confusing. But so the p-value is less than 0.05 that says it's not symmetric. If the p-value is above 0.05 that says it is symmetric. And so the distributions are all symmetric enough, at least according to this p-value estimation from mu, which is good in terms of like cosmology estimation, at least. Yes.
So this is like a distribution of p-values, and we're trying to test whether that distribution is symmetrical.
Yes. It is kind of confusing because it's a distribution of probabilities. It's not necessarily just p-values, but I know it is also called p, which is confusing.
So yeah, so for the top right.
Yes.
So you said that okay. So you are okay. So you're doing something significant. We're discussing that. So just one can see. Yeah, this is like more of a it's more technical thing. But I think you said that you did a case test on PM on Ana-Sofia.
Yes.
But I think the case test requires that the two samples that you are comparing they need to for its validity. So for example, so the two samples of distribution I'm trying to compare, I need those two samples to be independent. Otherwise, I guess the case test does not have validity. But I think there are some tests that explicitly can test the symmetry of the distribution. So maybe I don't know. Might be a suggestion that you can just subtract 0.0, 0.5 from the p-values, and there are some non-parametric tests that just test for the symmetry.
Sure. That's a good point. Yeah. So this whole chaos test on P in 1MSP business, this was said, it was in the paper that I showed, which is why I did it. But I agree that there are other ways to test if the distributions are symmetric.
It would be interesting to compare.
Yeah, that's a great point.
Yeah. Okay, Lina, you can ask.
So the truncated normal that you're using, Ana-Sofia. So do you parameterize the where the cut is, and do you sort of allow for that to change? And if so, what do you find?
We're enforcing that the truncation happens at 0. Is that what you're asking?
Yeah. I mean, no. So yeah, at what part of the Gaussian do you set the truncation point?
How far away is the peak?
How far away is the peak?
The peak of the
Gaussian. How far away the peak of the Gaussian is in your truncation model from the truncation?
I mean, we're just truncating at 0. And so for every distribution, the peak is different distances from 0. And
so you're letting the peak.
Yeah, so if the distribution is very close to 0, then it could cut close to the peak. Or if it's further away, it cuts less close to the peak. And if it's very far away, it's not going to cut anything at all.
How do you determine this?
Okay.
That's, I guess.
Well,
so that's the value of the AV. That's the the value of the AV that you're reporting in all these plots. That is the peak of the distribution.
That is a great point. That's something that we have talked about a lot. The AV that I'm reporting right now is the median of the samples. However, you could argue that the mode or the peak of the distribution, because it is skewed, could be a better estimate, point estimate of AV. And that's something that we've also talked about.
Yeah, right. You're clearly biased if you take the mean or median of that.
Yeah. In practice, I have also tried taking the mode. And in practice, I found that taking the median gives me better results in terms of these biases. But I agree that theoretically, the mode is a better estimate. And it's something that we've talked about a lot.
Yeah, thank you.
The more I think about this, the more worried I get. Is it the standard practice in the supernova cosmology business to have truncated dust distribution?
I don't think so.
Because I really think that could make a bias of a few hundreds in AV. And it would be distance dependent, right? Because it's magnitude dependent. If you have a faint supernova, you know, everything's less well determined and squished out, and that truncation matters more. If you have a bright high signal noise supernova, you've got a very tight distribution, you're probably not even truncating it. So now you've got this bias that is distance dependent that is probably big enough to explain the Hubble tension.
Okay.
Right, like, no, I mean, I really think it could be catastrophically bad to truncate AV values. And if that's what that field does, then the thing we need to do right now is go reverse engineer all their papers.
No, but that's interesting point. That's enough to explain the Hubble tension. That would be interesting. I mean, how big bias do you need in order to explain it?
Yeah, well, hundreds. I mean, it's confusing, right? Because getting AV wrong means you got the color wrong, you get the correction for the, you know, like you get a lot of things wrong once you have all the colors wrong. And so it's not as trivial as just saying, oh, we got mu wrong by 0.02, therefore the distances are wrong by, you know, whatever.
Yeah, but I think this AV was even in untruncated case biased, right? When you had this MCMC estimates.
Well, but MCMC is also making assumptions it's not negative, right?
No.
MCMC is using the model that uses the exponential prior, so it's good.
Okay. So it's not.
So I think if I can just can I? Do you mind if I interject here?
Yes, please.
So first of all, most of supernova cosmology doesn't even acknowledge that there's dust. Basically for the last 10 years. Yeah. But then I think you know, in terms of I think you said the right thing earlier, that you would say impose the positivity on the physical parameter at the point of inference. And so what I want to emphasize here is that we're not estimating AV as an intermediate step and then plugging it into some other formula to determine mu. We just have a posterior where we're marginalizing over AV to get the marginal posterior in mu. So that is the point of inference. We're marginalizing over a full posterior, and we're sampling over the full posterior, marginalizing out AV to get the posterior in mu. It's not like we're taking an estimate AV, forcing it to be positive and plugging it into some other equation. So I can see where you could.
Worse.
Sorry?
I'm agreeing that would be worse if you were doing that. I'm not sure that gets you off the hook entirely, though. And the evidence for that is the plots that showed the bias relative to truth, right? And there was a significant
AV was always biased.
Offset.
Yeah, that's true.
Right, it's offset and it's dependent on, right, it's not, there's not really an offset here, but there is here. If I really look at the right thing.
This is AV.
Sorry, I want AVs, okay.
So the MCMC will always, even with MCMC, because you have a positive parameter, your posterior is always going to be positive. So as your positive parameter goes to zero, close to zero, your posterior is always going to spill over the positive side. So yes, there's always going to be a slight bias to, say, the posterior mean or posterior median. But I think if we care about mu, you could see we don't have a bias in mu because I think the marginalization over AV takes care of that in the right way. Yeah. So, yeah, I thought about that.
Are you saying there's no bias here? Because I mean, it looks to me like the center of the blob here is 0.05 or 0.1, whereas here it's at 0. And so I'm very concerned about that tilt. Anyway, we should let it go here because we've gone over time. But
yeah, let's see. Yeah. Well, okay. Let's conclude. Jean-Louis, you have any comments?
No, just once you conclude this part, we need to move on to talk a little bit about other possible project for the other two students.
Yeah, it's a little bit late. I just worry, but because it's 1:20. So we have